Alright, time for the draftphysics.com. Debatephysics.com also, but as stated, the debate is a bit thin. So we have another comment from this channel 321 guy. And, alright. Just keep playing the game. Huygens was talking about collisions of hard bodies of any mass in general. Well, says you. When he talks about collisions of equal masses, he states that explicitly. Well, prove it. Okay, and let's not forget that he understood. Now, you're saying he understood something. I'm saying if either one, Newton or Huygens, actually believed you could increase momentum, momentum was still a thing back then. That's perpetual motion. It becomes very realistic. So why would he say perpetual motion isn't possible when in these collision experiments he's making extra momentum? So I'm saying, you're saying he understood. I'm saying I don't think he could have to that extent. Now we're talking about 1650 here, all right? So, got to cut these people some slack. They didn't have video cameras. you know, the conservation of mv squared in collisions of hard bodies. So again, he clearly stated it. I don't know how well he understood it, and clearly the implications of it are disastrous in terms of this idea of creating free energy. The lever demonstrates that. So again, if you believe levers conserve momentum, then they are creating free energy. All right. You said 1 million units of motion collides with 1,050,000 units. Yes, I gave you an example of what makes the whole thing ludicrous as a law. This subtraction math, okay, doesn't work. Clearly, I could bang something that, we could make it whatever. We can make it 500 and 550. Do you really think that collision only produces 50 out if it's elastic? I mean, it doesn't work. According to your theory, one object stops and the other one leaves with 50 units of motion. So that's my point to you. You can't counter the point by saying, yeah, I'll read what he says. I'm pretty sure that cannot happen in an elastic collision. So you're conceding my point. That it doesn't work. That you can't do this subtraction math and make sense out of the universe. It doesn't work. Damn. The math does not allow it. So what math are you talking about? Your math, okay, says that's exactly what must happen. So what math are you talking about? I mean, fuck, you can't extrapolate from 50 and 150, and subtracting the two 50s and saying they cancel each other and you're left with the 100 going out. You can't extrapolate and recognize that all I have to do is change the numbers of what's different going in, and it creates this paradox where you can destroy 99% of the momentum. What would happen in an elastic collision is that both objects would be moving after the collision. Yes, who's arguing otherwise, except your Newton's cradle proves exactly the opposite. So why are you saying it? I mean, I would have thought, yes, okay, both objects will be moving. Well, you're pointing out how obviously 150 goes in and 50 goes in. 100. No, 50. 50 goes in and 150 goes in, and the 150 stops dead. All right, and the 100 pops out. So that's the actual experiment. So that we don't disagree on, right? That's a physical demonstrated fact. But the argument is that yes, again, what's the principle here? You're saying it's because of subtraction math. I'm saying if you think it's subtraction math, then it doesn't work as soon as I start making the objects have more and more momentum, because you start destroying bigger and bigger chunks of momentum. And the difference, if opposite directions, are the sum if the same direction would be the same as before the collision. So again, you're saying it again. It's not true. So you're just conceding it wouldn't happen. You're conceding that if I did your math on my circumstance, 1 million in and 1 million and 50, the only difference is the 50. The only thing that survives the collision is the 50 by your math. I mean, come on. I mean, can't you play fair ever? All right. So, I mean, it just misses the entire argument. You know, just threw it in the garbage and said, I'm just going to talk gibberish. Where, yes, it's an absolute truth that your math says I destroy 2 million units of momentum and only conserve 50. That's what your math says must be the result. Your theory says that must be the result. Explain how your theory doesn't say that must be the result. All right. You said subtracting makes sense if you are allowed to start with negative numbers. That is, if you recognize the directions and concede that both directions have to be conserved. The energy going this way has to be conserved with the energy going that way. But that goes against the collision experiments by Newton and others. So again, says you. Okay, so what collision experiments by Newton? He doesn't detail specific collision experiments. He makes general statements about collision experiments. All right. It also goes against many other things stated by Newton. Says you again. So fuck that. I mean, what Newton explicitly said was twice the force, twice the velocity, 3 times the force, 3 times the velocity. That's what he fucking said. All right, and not indicating he thought there was any hope of this exponential growth, based on your theory. Also, Newton said that his rules for momentum are the same for all objects. Yeah, and again, what rules are of momentum are you citing? So what explicit rule did he state other than the amount of force that goes in is the same as the amount of force goes out? That's the reading of Newton's statement. Again, it's how you're interpreting the statement. Hard and soft, elastic or inelastic. So again, whatever. So then he has a quote. I must add that the experiments we have been describing, pendulum collisions, by no means depend upon the quantity of hardness. Do succeed as well in soft as well as hard bodies. It's just talking about the fact that you can use different kinds of elastic material. Now, obviously, he pointed out how, glass is better than steel. So he observed all of that, but he also used, which you could argue was plastic or, other materials. Plastic's the wrong word to use. It didn't, like ember. But the thing he didn't do, the big distinction is in the inelastic collisions. They hadn't fully recognized that there's still a lot of motion in the object. Now they speculated that the turning and twisting and movement of the objects is where the energy goes. Like if you hit 2 pieces of clay into each other, they deform, and the deformation equals their energy. So again, in the case where we took inelastic objects with 1 million momentum and 1 million momentum, you can expect them to do a lot of deforming. Another big difference between you and Newton. Says you. There's no difference. Fuck you. I mean, it's just such bullshit. And another similarity between conventional physics and Newton. There's no similarity. So again, you can keep saying there's a similarity. His laws of physics are about conservation of momentum all the way through. The first, second, and third law are all conservation laws, and it's about conserving momentum. Nowhere does he mention NV squared. Nowhere does he talk about, hey, look, you can make a bunch of free momentum. So, no, it is not consistent with conventional physics. And there wouldn't have been a visa controversy. There wouldn't have been, France wouldn't have had a contest to resolve the issue. None of that stuff in the real history would have happened if Newton agreed. So just keep rewriting the history and putting words in Newton's mouth. Let's see. It starts to make sense why they call it Newtonian mechanics. I really can't understand how it makes any fucking sense if you're at all honest. Why was Leibniz writing Kings and Queens about how Newton and Descartes were wrong, okay, and how it must be resolved? Why was this an important subject if Newton agreed? I mean, it's just such a lie to pretend there was agreement that MV and MV squared are the same fucking thing. They're not the same thing. All right, so we'll play the Gosling has made another video with, gigantic flaws in it, of course. You can't, he just won't. He won't. That's the simple word. He just won't bother perfecting anything. All right, so let's see if I can draw this. Pen goes the right way? No. I can't tell because the frame rate's too damn slow. Anyway, all right, so the point I pointed out in the previous video was that, okay, you hit equal masses into each other, you conserve 100%, no problem. Okay, 100% in, 100% out, same direction, no complexity. Then when you're doing this 1 into 2, okay, then the theory is this goes back with 1/3 the velocity, okay, and this also has 1/3 the velocity. So it's the 1 to 2 relationship where you end up with the equal velocities going both objects, okay, because the one here, clearly this one weighs twice as much, that's 2/3, this is 1/3, you conserve the momentum, makes sense, okay, works. And then the 1 to 3, okay, as pointed out, the expectation, so you're increasing this way, right? So you're just saying, what's the reflection? You got 0 here, you got 33% of the momentum, okay, and now in this case you're going to get a 50% of the momentum is coming back. So obviously that would be twice the velocity for this object. All right, and obviously with the 3 mass it would be 1/3 of that twice, or 1/6 of the velocity. All right, would be the expectation. Now clearly the less that goes this way, so if you're less than 50% you only get 40%, well then the 60% is over here, so now it's not 1/6, it's 1/4, and this ends up being 1/3, and so you get a much more complicated division. And the idea would be is the floor mass would be something around the 66% coming back, and only 33% going this way. And then the 5 mass would be getting closer to your disaster math circumstance where all of the energy comes back. You get 100% of a reflection, or 98% or something, and you get a very small reaction, if any reaction at all, once the mass gets heavy enough. 5 times the mass, 6 times the mass, somewhere in there. So these numbers aren't perfect. All right, so just understand that. But measuring this with the 1 to 3 halfway back is exactly what both theories predict. Okay, so half the velocity coming back. Now, he obviously doesn't get half the velocity, so the rest has to go forward in the other object. And because of the way he filmed it, we can't, again, see anything useful. So we'll go to the video and attempt to clarify. So I shall be back. All right, so he did 2 videos. The second one was in 1 minute and 40 seconds or something. Pretended it was filmed better when it was filmed worse, actually. So So he doesn't have it. He doesn't have the camera centered on the point of impact. So that's the first. Oh shit. So he's just watching the rebound ball instead of watching both, and so it's just not as interesting as it would be. I've turned off the sound, but we really just don't need him. Now you can see that it's obviously not oscillating consistently, so they don't hit always in the middle. And that's because it's just such an obvious and simple error. I mean, Newton's cradles are made a certain way, so you can just look at one and see that it's, that the strings are designed a distance apart from each other so that the balls, are going to be just in contact with each other. So what he's done is this, one contact point, and he has them hitting each other this way, so they're not hanging straight down. So as soon as he moves this ball up, this ball moves this way, obviously not centered, so it breaks the point of impact and it screws up the distances, and therefore they don't come back at the same time and hit each other again. They hit early or late, which just ruins the cycle kind of idea. And the perspective, again, the view we're getting, the center is here. Okay, so he's got the camera, off center, and that means that as this swings, that parallax thing happens where this is more distorted over here, and over here than it is here in the middle. And the middle isn't the middle of the swings of the pendulums, so it's off that center. Now, he doesn't also draw the whole circle and just have the thing, so the drawing isn't much use, and it's clearly not perfectly consistent with the video, in the sense that the ball is either above or below the line. It's not always in the same place. So it's not really measuring the center of mass and the movement of the center of mass. So these are some of the little things, some are big. Not getting the centering thing right. This mistake. Easy to fix. So he should have a distance. He should have them so they're just barely touching each other. So when you pull this one up, this one doesn't move at all. And he didn't do that, and therefore the thing doesn't consistently cycle. Now, from the viewing it, you could draw all kinds of conclusions, in terms of what it superficially looks like. But again, I'm going to argue that looks like isn't is like. And so there's still error in there. All right, so let's see when he gets around to picking it up here. So he's doing his little jabbering. Okay, he's going to talk. And here's the actual experiment. So he's put a peg for marking where to drop it from, but it's still, he's still holding it with his fingers. Still not exactly a consistent release point, which is, not great. And again, this is, the center of the frame is here, and the center of the pendulum arc is here. And again, there's no complete circle on this other side, so we can't really tell how high this one's rising above that center point. All right, so the simple point is we both agree that this ideally would come back halfway. Now it doesn't. And so, but that could be because this mass isn't quite 3 times. It's a little less than 3 times. And he doesn't think that's important, but yeah, it is kind of important. All right, so anyway, I have the right thing on here, right? Yeah, you can see pretty much all of it. All right, now we'll do the frame thing. All right, so there it goes. 1, 2, 3, 4, 5, 6, about 7 frames to go that whole distance. All right, now you could say right off the bat when this reflection happens, you know, this ball was a little bit forward, but obviously this one looks like it's moved more distance than this one, okay? But you really can't tell because it's, you know, pretty blurry frames. But as they move away, the argument would be is they're not moving the same velocity. This is moving the faster velocity. This is moving a slower velocity. Which is consistent with the fact that this weighs more and this weighs less. All right. So it almost, you know, it has to get up here to be really consistent with being 2x the velocity. Now this is pretty far over, but again, that's because the center of the frame is over here. So it looks like it's further over because of the parallax, but, you know, who knows how high it exactly is. Can't see it, so there's no point, right? So what he needs to do is film straight on. You know, there's kind of like no point in not watching this other object because that's the one you're saying has 150 momentums rather than just 50. My argument is half the momentum in this case goes this way, consistent with the 2, and the other half goes with the heavier object. And then they come back together. Oh shit, I didn't want to do that. Okay, we saw that part. And so it goes almost to the 2, but not quite. Alright, and they're coming back together. And obviously they're not going to come back. They're not going to hit at the center. So this one's lagging behind because he hit it too early. Because it moved its position. When he took the light ball away, the heavy ball moved over and changed its position. So it's got hit further back, technically, from the other one's perspective. And so they're not hitting at the same center because he has these 2 chords tied to the same location, or at least too close to each other. Damn it, I did it again. I was supposed to do slow motion and I didn't do it. So you can see the other ball is moving a lot because when you move the one ball, that one moves back down, and that's what you wanted to try to avoid, actually. Alright, so now they're coming out. Now they come back together. So it's a little short of 2, which means the other ones have got a little more than half. Alright, and then this impact, this one stops, but look where it's stopping. It's obviously stopping almost an inch from the center line, so it's hitting way too late. Alright, and this will go all the way back up to almost the starting point, and then it comes down. So this one's still moving. Now it's going to be forward of the point it should have stopped at, meaning it still had some of the energy. And so that's what's causing the cycle to be out of the let's see, what's the right word for it? So it's causing the there's a word for being in sequence, out of resonant frequency. Okay, so the 2 aren't moving at the right velocities from the right center point. The center point keeps changing. Alright, now it does look like this one's going the same speed as this one. I mean, it looks like the same distance, but again, what it looks like is because the frame isn't centered. So that appearance could be very deceptive. But it is high off the surface. You know, you got to say it appears to have more than 1/6 the velocity. But again, then you'd still have to account for, well, then why don't I just increase these masses and have a smaller and smaller difference between them in terms of their momentum, and you're going to get these crazy results where you put 500 momentums in and you only get 3 out or something, and that's just not going to be possible. I mean, by their theory, by the raw theory, I could move these two objects into each other. I could give them velocities of 500 momentum going this way and 500 momentum going this way. So 1/3 the velocity here because of the 3 mass, and 3 times the velocity on the other side, and have them collide and have some expectation that only the 3 difference between them. One had 3 extra momentums. Clearly, when 2 hard bodies hit elastically, they have to conserve the momentum they had going into the collision. Whatever went into the collision has to come out of the collision. You can't have 300 momentums and 100 momentum car crash and have just 200 pop out. Can't happen. So that's why I know there's likely enough flaw in this experiment to account for these differences. So again, they're not going to come back together anywhere near the center. See, it's way off the center now. So it's, it's even further to the one side. So he's got to fix that. And such. And now they're going to hit way forward. And so you really can't judge anything. My opinion. Nothing useful there. Not useful enough. All right, that's probably enough of an argument. Again, so I just, I just restate my point. Do they think levers don't conserve momentum? And second, do they think it's actually possible to have 1,000,000 momentums going this way and 1,050,000 going this way, and that they hit and only 50 pops out? Because if they don't think that's possible, then there's something wrong with the theory they're applying. Their rules aren't consistent. It doesn't continue to work. And why wouldn't it continue to work? You have to explain that. And I could go back to, another example of where it just becomes impractical to think what they're saying is true, because I could go back to the anvil argument and again just point out that by their theory, I have a hard surface, and okay, move that over, and I bounce a ball bearing against the hard surface, and it really depends on how hard the surface is, right? So if I don't use hardened steel, the steel actually dents a little bit, and I only get maybe 5 bounces. But if I make it really hard, I can get up to 200. Okay, so the ball will just keep bouncing back, losing a little bit of energy, but just bouncing back, losing a little bit, losing a little bit. But you can imagine that it doesn't lose much, and it just gradually goes down and lots of little bounces. All right, but the point would be is with each hit, I'm supposed to believe that 100 momentum went this way. Let's say it's 100 momentum from this height. And then it was 99, and then 98, and then 97, and then 96. You can just say, it just starts to add up, and I end up with maybe 30 times, 3,000. And I started with 100. So 100 bits of energy goes in this direction, and I end up with 30 times the momentum pushing this surface. And so how realistic is that? I'm just saying I don't think it's realistic at all. And if I turn that experiment this way, hello, where are you, camera? There it is. Okay, so the pendulum bounces into this hard, heavy object, and we're supposed to believe that with each time it hits, it's putting 100 momentums into the other object. So if I can get it to bounce back with almost 100, that is, if I use this 6 or 7 times as heavy ball bearing, the ball bearing ends up going back pretty far, indicating that I have achieved the full rebound. And I'm supposed to believe that then I can keep hitting that object and keep giving it 100 momentums each time I hit it. Maybe I can hit 10 times that way, maybe 100. And obviously that doesn't make any sense. Can't work that way either. All right, so we'll call that a video and such. So yes, fix how you've attached the pendulums and film the whole thing. Or you could film it both ways. He doesn't have to. He could film it so we could see the whole arc, and then film it where we just see, and then just promise to drop it from the right location, and then just show us both the 2-inch marks from the center. So he could film it so we could see the whole thing, and then we could see just this isolation from the 2 marks, the 2-inch marks, and see if both balls reach the 2-inch marks. Because if they're going the same velocity, they would have to. Okay. And I certainly predict they wouldn't, but we'll see. Alright, so enough of a video now. So till the next time and such.